что я появится.
Хорошо, спасибо. Спасибо.
Все, убили.
Okay, good morning. Good morning, everyone. Before to start, so today's topic of today's lecture, dispersed system and colloids. If there will be enough time, I will give you some information for pH because of there are some, I don't know why, there are some problems with the understanding of this topic. No, so dispersed system, first of all, they are without teacher's help, it's hard to understand. Okay, so dispersed systems. All solutions we discussed before, they were true solutions according to their homogeneity. Colloidal chemistry, it's a branch of physical chemistry that studies heterogeneous dispersed system. What is the difference between? They are same composition of solution, known now as dispersed system. Dispersed system is the same solution, but dispersed phase solute is mildly and uniformly distributed in dispersion medium, solvent. To be homogeneous or heterogeneous, just different in dispersed phase particle size. True solution, we know that diameter of solute particles less than 1 nanometer, 10 power negative 9 meters. For coarsely dispersed system, they are unstable heterogeneous solutions, suspensions, their diameter of solid particles more than 100 nanometer. This means that they are big enough to see them with the naked eye, and such systems quite unstable and precipitate very fast. And between these two, between true solution and coarsely dispersed systems, they are colloidal solutions. Diameter of solid particles for them more than 1 nanometer, but less than 100. That's why with the naked eye, these particles we can't see. If the diameter of particles becomes almost 100, we can see this as a muddy, but not particles we can't see still. And they behave unique way because of the size. So as all solutions in the world, so let us start with classification. Colloidal solutions can be defined as a highly dispersed heterogeneous systems in which at least one substance is in colloidal state. Colloidal state means diameter of solute particle more than 1 but less than 100 nanometer. Why it's so important to understand at least one? Let us take our blood as example. We know that there are a huge number of different substances dissolved, as some of them true solution nature. There we have ions can be found, low molecular weight compounds, but there are some number of particles present is in colloidal state. For example, even cholesterol. Even one component change the classification of the blood. It's colloidal solution. So about classification, for all solutions, as I told you, in the world, we can classify them according to the aggregate state, physical state of solute and solvent. Here more correct, as we're talking about heterogeneous system, to use both dispersed phase and the dispersion medium. So there are possible 9 types. So solid, dispersed phase can be gas, liquid, solid, and dispersion medium solvent can be gas, liquid, solid. When we combine these two, dispersed phase with a dispersion medium, possible to find 9 types, but gas and gas always homogeneous. That's why heterogeneous systems such type not exist ever. So, but gas can be uniformly distributed in a liquid to make liquid form. For example, whipped cream, it's a I know, form for hair treatment, shaving form, right? Bath form, liquid form, that means gas in liquid, bubbles of gas in a liquid medium. Gas in a solid medium, it's the same solid, looks solid. It's a solid form. It's like something like porous material. And here can be pumice stone, sponges, activated carbon black can be example of such type of heterogeneous system. Liquid disperse phase and dispersion medium, gas, liquid or solid. Liquid in gas seems like drops of liquid substance in a gas medium. This mixture known as a liquid aerosol. As example can be fog, cloud, sprays from cones, doesn't matter, perfumes, right? Liquid emulsions. To produce such heterogeneous system, they are supposed to be immiscible liquids. If they are liquid miscible nature, they are never heterogeneous. And for example, milk, it's a dispersed, it's a heterogeneous system. Oil and water, stabilized by proteins. So paints also can be. Liquid in solid. It's a solid emulsion. Looks like solid stone, but with a liquid, drops of liquid there. An example can be pearl, opal stone, but there can be examples of such type of colloidal solution. And the last one is solid in gas, solid in liquid, solid in solid. Solid in gas, it's a solid aerosol. Atmospheric dust, smoke, everything such nature, no, I don't know, sandstone maybe. Solid in liquid, it's a sol. Please, SOL, sol. It's not short for solution, not short for solid. It's not a short at all. It's a word, means that this is colloidal solution, solid in liquid. Usually they are ionic solids. So, colloidal suspension here also can be example of such type of colloidal heterogeneous solutions. Examples, any inorganic colloidal solutions, sol of sulfur, sol of gold, colloidal solution of toothpaste also can be its colloidal suspension. Solid and solid, solid suspensions, no colored plastics can be example of such. The easiest classification, but necessary to know the name of the type and put any example. So next one, classification, very important, because then according to this we will produce solutions different way. Their stability can be described and the method to prepare. So classification of colloidal solution according to the interactions between the dispersed phase and dispersion medium. So and here two types, lyophobic colloidal solutions and lyophilic colloidal solutions. Phobos means hate, philic means love. Lyos means liquid. If we're talking about water as a solvent, as a medium, they can be known as hydrophobic or lyophobic. They have a very slight or no attraction of dispersed phase to the liquid dispersion medium. That means their opposite nature is supposed to be or insoluble substance or immiscible liquids, opposite nature, because of, like dissolves like. So they are not stable themselves, can't be prepared directly by mixing dispersed phase with the dispersion medium because of the insoluble in each other. And they need to be stabilized if they are prepared with any other except direct methods. As stabilizing agent, mostly we use electrolytes for inorganic lyophobic colloidal solutions. For example, it can be colloidal solution of any metal, non-metal, or insoluble salts. and lyophilic colloidal solutions, or hydrophilic if we're dealing with water as a medium. They show a very strong attraction of dispersed phase to liquid dispersion medium. Because of this, they're very stable. They're stable and can be prepared directly by mixing dispersed phase and dispersion medium. They need no stabilizing agent usually. For example, solutions of protein, starch, and nucleic acid. Starch soluble in water, we know, but the problem starts to appear because of the size of the solute of these particles. As at higher molecular weight compounds, the molecules are quite big, and their molecular weight much more than 5,000 grams per mole. So that's why, being soluble in water, this compound can't behave as a true solution. It's a true solution according to the nature of substance to be dissolved. It's supposed to be homogeneous, but size of molecules too big. And that's why their behavior, molecular kinetic behavior because of the size, will be same as for colloidal solutions. So if they are for lyophobic colloidal solutions, no, lyophilic, as I told you, they can be prepared directly. I will mention this then. Substances opposite nature, lyophobic, they are insoluble salts. How can it be possible to prepare colloidal solution? Looks absolutely transparent and stable enough to not precipitate. So, because of colloidal solutions are between true solutions and causally dispersed, from 1 to 100 nanometer their size. So we can prepare them two ways. We can take causally dispersed with diameter of particles more than 100 nanometer and somehow make these particles become smaller. It's dispersion methods. And aggregation or condensation methods means we want to prepare colloidal solution from true solution by particles growing. So let us see how it's happening. Dispersion methods from causally dispersed, aggregation methods from true solutions, and let us see what methods here can be used. Dispersion methods. Again, reduce larger particles to colloidal size. And not enough just to reduce particles, necessary to deal with a solution, causally dispersed, but solution, their dispersed phase and dispersion medium already should be in one mixture, and stabilizing agent already must be there to stabilize the colloidal, hydrophobic colloidal, say, moment of appearance. So here are possible to use two types, not even three, but two mainly. They can combine in one. It's a mechanical and ultrasonic disintegration. Colloidal mills or ultrasound. Again, in both cases, we can't use just solid dispersed phase and a liquid dispersion medium. If we will mix them even with a good proper size of dispersed phase particles, they will not form the colloidal. They're insoluble. They're opposite nature. They're no attraction of dispersed phase to the dispersion medium. That's why it's supposed to be solution causally dispersed and electrolyte as stabilizing agent. And electric sublimation by electric arc. It's for colloidal solution of metals just. If we need to prepare a colloidal solution of gold, ruby colored one, we will make two electrodes of same metal, and the electric arc will help them to be disintegrated. And if their stabilizing agent is present, their colloidal solution appears. Peptization, as you see here, it's not numbered. Because of this method is for lyophilic colloidal solution. It's a direct method. It's a chemical dispersion of precipitates by shaking them with the additives of electrolytes or surface active substances. It's a direct method. We take precipitate, we mix this with the addition of stabilizing agent, and as a result, the colloidal solution appears. This is possible for lyophilic because there's supposed to be at least some good enough affinity of dispersed phase, attraction of dispersed phase to dispersion medium. Aggregation methods or condensation methods allow to make particles of colloidal size from the molecules. So that means true solutions can be sourced in this method. And here possible to use physical condensation or chemical condensation due to what we do. Either a chemical reaction as a reason of growing up the particles till colloidal state, or if there are physical methods enough. So physical condensation can be few types. It's a condensation from vapors known as excessive coolings. So this method it's seldom, no, so can be used only for some colloidal solutions, gas and liquid, for example. No, so we can prepare colloidal solution of mercury as a liquid metal such way. Solvent changing method acceptable in a case when substance good soluble, no, as you remember, like dissolves like, doesn't mean that polar substance is soluble in every polar liquid. No, we have huge number of polar substances soluble in one polar liquid, but insoluble in other. And this method possible to use for these substances, such something like California. Solid, polar, soluble good way in alcohol, but it's soluble in water. So what we do? We dissolve this substance, California, in an alcohol to produce true solution. And then little amount, we need excess of water, because of then when we add alcohol solution of California in water, excess of liquid becomes a solvent. So we need excess. So little amount of California alcohol solution we add to the water excess, and alcohol goes as a miscible liquid in water, and California there becomes insoluble, and it forms muddy, it forms a colloidal solution. If we will mix great amount of alcohol solution and water, we will get California precipitate. And chemical condensation or chemical aggregation. Here more correct to use this word aggregation, as a true solution particles due to chemical reaction supposed to form precipitate, but because if we do something with the reactants, they are not precipitate formed but colloidal solution. What way? Any chemical reaction can be source of this method. Anyone. Doesn't matter what type of reaction. Is it redox reaction or non-redox? From non-redox, is it neutralization reaction or any decomposition reaction? Doesn't matter. Any chemical reaction if one of the product insoluble. From true solution, there was true solutions left side. Among products, supposed to be precipitate. If their true solution is formed, weak electrolytes but not precipitate, colloidal solution, such method we can prepare. And one of reactant excess supposed to be to form medium, and this excess of electrolytes supposed to be stabilizing agent. So let us see how it looks like. For example, double decomposition reaction, barium chloride with sodium sulfate. Test reaction to identify barium or sulfate ion. So white precipitate of barium sulfate, it's a sign that there was barium or sulfate ion among initial. So if we will mix 1 to 1 as it's supposed to be according to the chemical reaction, we will get precipitate and that's it. But if we will take barium chloride excess or sodium sulfate excess, what's mean excess? That means few drops of one of reactant and 10 ml, 5 ml of the second. Deficiency, grade 1 of one of the component, excess of the second. So what we will get? We will get colloidal solution. It will be absolutely transparent solution of barium sulfate colloidal, being insoluble there. Hydrolysis is one of the methods to prepare colloidal solutions of some, like iron hydroxide. We know that iron chloride with water due to hydrolysis forming precipitate brown-red of iron hydroxide. But if there will be excess of boiling water and few drops of iron chloride, there are no precipitate. We will get solution looks like true, absolutely transparent, and the black tea color. So after solutions prepared, due to what methods were used, there can be different impurities. And before to apply this solution before to check their chemical behavior, physical properties also. We need to purify. So there are four major types of purification, because there can be more. There are filtration, dialysis, electrodialysis, and ultrafiltration. Let us see purification from what methods there, from what impurity there. It starts with filtration. Filtration is a purification of colloidal solutions from coarsely dispersed particles. That means from particles greater than 100 nanometer size. Such particles can't pass through ordinary filter, a colloidal passing because of their size less than 100 nanometer. So this is the way. If there are something like colloidal mills is used or ultrasonic disintegration, so if they are not complete and there are still some big size particles present, we use filtration to separate this impurity from colloidal solution. Dialysis, it's a purification of colloidal solution from particles of molecular dimension. It can be non-electrolyte, can be electrolytes, but electrolytes, from electrolytes impurities, we can purify with the help of other method. Electrodialysis, you will see that, and it's much more fast, and that's why more acceptable in this case. But it doesn't mean that we can't use dialysis as purification method from impurities of electrolytes because of their molecular dimension, less than 1 nanometer size of particles. How it looks like, then we will see. Take a look. Dialysis, it's diffusion through semi-permeable membrane. Cellophane bag, for example. Membrane only less than 1 nanometer particles can pass through, but colloidal particles cannot. So what is there we do? If we need to purify colloidal solution from some impurity, for example, glucose, this is non-electrolyte, but true solution. It's less than 1 nanometer particles there. So what we do? In cellophane bag, this solution we place in cellophane bag and dipped in a pure dispersion medium. For example, water, if it's aqueous solution was. Like aqueous solution of starch with some presence of glucose. We need starch colloidal solution, pure one. So water in, water out is an essential thing. Why so? Because of gradient of concentration should be the biggest possible. So what's happened? Diffusion is spontaneous process of movement of dissolved substance, that means solute, from higher concentration to lower concentration. So that means if we dip cellophane membranes to this bag with our colloidal solution and glucose, the impurity, glucose will pass in through membrane because of it can do this, its size is quite small, and it goes spontaneous to dispersion medium outside because of equalizing the concentration. And if water always, water in, water out, that means pure water without any glucose will be always outside the cellophane bag, glucose will move till no more glucose left inside the bag. Gradient of concentration always outside the bag supposed to be zero concentration of impurity. In such case, purification happened completely. So dialysis is quite slow process. In all cases, diffusion through membrane happen not so fast, but it's very effective. And it's used in medicine. Anyone who heard, I hope, hemodialysis, it's artificial kidney. It's removing of waste particles such as urea from blood. The idea is still same. The mechanism quite more complicated, but the idea is still same. Dialysis solution outside. It's not pure water, definitely. We need just some waste substances pass through the membrane. And with time, purification of blood happened with very, very good result. Electrodialysis, it's a purification from impurities of electrolytes. From non-electrolytes, we can't use this method to purify because of its, as it visible here, we need electrodes for this method happen with a good this method happened, let us say so. Two electrodes dipped other sides from membrane. Same here, same membrane, same impermeable nature, only impurities can pass through. For example, impurities of sodium chloride, true solution, dissociate completely and present as separate ions. So colloidal solution inside between these two membranes, and if it's same starch, for example, or any other colloidal solution, when we dip electrodes, sodium will move to the one electrode and chlorine to the other, passing through membrane spontaneous. But colloidal particles can't pass through membrane. Even if they are charged, membrane will not allow them as their size quite big. What is ultrafiltration? Now, ultrafiltration is more correct to say it's the method to concentrate colloidal solution, because of it's a type of filtration through the semi-permeable membrane with the ultra-porous pores. It's a pores there much smaller than for just filter, and our colloidal particles can't pass through. But solvent can, and pressure gradient helps solvent dispersion medium pass through. Take a look how it looks like. There are two pictures, but demonstrate same. Pressure gradient supposed to be, or our dispersion medium will not pass through such small porous membrane. Under the pressure of 4-5 atmospheres usually, dispersion medium pass in, and above the membrane, colloidal solution becomes more and more concentrated. Till separation happens completely. If we will not stop in time, we will get above membrane dispersed phase particles, and the dispersion medium will be another flask. So after our colloidal solution purified, they're pure now, we can see how they behave. We can discuss now their properties. And there are three types of optical properties, molecular kinetic and electrokinetic properties. Let us start with the optical. Now, according to the name, it's supposed to be clear that they are somehow dealing with the light different way than true and causally dispersed. And it's really truth. If light beams, strong beam of light passing through true solution, as they are small size particles less than 1 nanometer, light just passing through, and we see nothing inside, just light passing through. If they're causally dispersed, they are reflection of light happen. Light can't pass through, it reflects because of big size particles. What can we see? We can start seeing these particles with our naked eye because of reflection of light. But light will not pass. Colloidal solutions, because of their size of dispersed phase particles from 1 to 100 nanometer, their scattering of light happen. As a result, we can see the beam of light inside the colloidal solution. It's a test to identify colloidal solution, to be sure that this is colloidal but not true and not causally dispersed. Strong beam of light, when it passing through colloidal, take a look colloidal solution of iron hydroxide, we can see the beam of light here. In some cases better, in some cases worse, but it's visible quite good. Class time, usually we use laser pen to show you what is the difference between true solution, water, pure water there, and colloidal solution of barium sulfate. Both looks absolutely transparent. This effect is known as Tyndall effect. It's a formation of visible cone when light beams passing through the solution, colloidal particles nature. About molecular kinetic properties. As according to this name, it's clear that these properties appears because of the unique molecular size. The size of colloidal particles from 1 to 100. That's why they have unique properties because of this size. The first of all, it's a Brownian movement, not typical neither for true solution, not for causally dispersed. As you remember from biology, Brownian movement is zigzag movement of colloidal particles in a liquid medium under the collisions of small molecules. It's a chaotic movement, we can't predict it, and that's why, because of the This movement is typical for colloidal solutions. Resulting force not looks down, and they are not precipitate, being heavy enough, being much more heavier than true solutions particles, but they are not precipitate because of gravity. Brownian movement, it's one of the reasons of their sedimentation resistance. Second set of properties, it's diffusion and colligative properties. But why they are so? Brown diffusion movement, diffusion and colligative properties we discuss as a sum typical for true solutions as well. Here the difference in a rate of and a value. Diffusion for true solution happens fast enough. For colloidal solutions, it's very slow because of the size of colloidal particles much bigger than for true solution. That's why diffusion also typical. There will be movement of colloidal particles from higher concentration to lower concentration, but it's happened too slow. Colligative properties. As you remember, colligative properties, they are independent the nature of the solute. They depend on nature of nature of solvent and number of solute particles. Because of colloidal solution, and they initially prepared taking deficiency of one of the component, size of them big, number of particles is very small, and that's why there will be very small value of colligative properties factors. No sense in something like vapor pressure lowering, we will see almost nothing. Elevation of boiling, depression of freezing point, too small to talk about, and they produce very low osmotic pressure. If to compare with electrolyte, we can't even compare, many times smaller. And one more property, sedimentation. Sedimentation is formation of precipitate. It's supposed to be typical for them. They should precipitate because of their heavy, but sedimentation resistance not allow them. If we somehow we will stop, if we will affect viscosity, if we will stop the Brownian movement, these particles precipitate same movement. So, structure of colloidal particles, lithophobic nature. To understand why these particles, they give us electrokinetic properties. Electrokinetics means properties because of their some charge present, the electrical doubling. Let us try to understand what's happened due to formation of colloidal particles. And I took here test reaction to identify silver. As you remember, silver nitrate with a potassium iodide forming yellow colored silver iodide precipitate and potassium nitrate as a second product. If they are 1-to-1, according to the number of moles, but if the excess of one of the reagent, I took now a silver nitrate excess, due to this excess, their chemical condensation method, chemical aggregation method, produces, during this method, we produce colloidal solution, are not heterogeneous, not precipitate. Excess, again, it's for many times more. 10 ml of silver nitrate and 1-2 drops of potassium iodide. In this case, only same, according to the balance coefficient, silver nitrate will react with potassium iodide, and the rest of silver nitrate will stay as an ionic medium, as a stabilizing agent to stabilize the colloidal particles. So what there happened? Leave some space, as you see, I left there are 3 lines, because of above I will indicate layers. So this deficiency of potassium iodide, when it's react with silver nitrate, there's ionic solid formed. Silver iodide, it's ionic solid. It's a real crystalline substance with a real crystalline lattice. And it can be visible in microscope, for example. It has some number of silver and iodide ions. Total amount of them equal to each other because of this crystalline substance. This particle is neutral, but it's not one silver ion and not one iodide in crystalline structure. It's a real physical body. That's why we use here brackets and symbol M, showing that some number of them, maybe 100 there, due to the size of crystal. These solid crystalline particles, real one with exact surface, it formed due to aggregation method. That's why it was named aggregate. Aggregate is a neutral solid crystalline. It's a unique solid, and that's why it will not attract any positively charged or negatively charged particles. But it wants to grow. Growing of crystals is spontaneous process. They always grow. Because of surface in such case becomes lower. So growing of crystal is spontaneous. How this crystal can grow? It can grow by absorption of ions already present in this crystalline. Adsorbed silver and iodide from surrounding, it becomes bigger. But the problem is we have only silver ions present in surrounding. Potassium iodide was one drop and it's already all iodide ions present inside aggregate. So that's why aggregate, according to Paneth-Fayence rule, it will attracts ions already present inside crystalline structure, but in excessive moment to be absorbed. What ions? Silver ions. So again, according to the Paneth-Fayence rule, only ions already present in aggregate, which is insoluble particle, inside the aggregate and in excessive moment will be adsorbed on the crystalline surface of aggregate. How many ions, silver ions, will be adsorbed? We don't know. It depends on huge number of factors. Concentration of reactants, size of the silver iodide. So a lot of factors. It's n, maybe 5, maybe 100, we don't know. Not some number. This dot, it doesn't mean that it's multiplied. This dot between aggregate and potential determined ions is just a dot to separate one layer from second one. Potential determined ions, they know why? Because of after adsorption, adsorption, that means on the surface. It's still solid crystalline, it's still solid, but now charged. This charged solid appears after adsorption of potential determined ions, known as nucleus of colloidal particles. Nucleus charged, in our case, plus N charged, can be negative if there will be other colloidal particle. So what we have now? We have solid, ionic solid, but now positively charged. Definitely it will attract all positively charged ions from solution. Interionic interaction. What ions they are present or positively charged and in excess, because of only excess ions stabilizing the structure of colloidal particle. Nitrate. They are nitrate or positively charged to the silver, and it's attract to the surface of nucleus to neutralize the charge of the nucleus. So how many nitrate there? If number of silver n, according to the formula, nitrate ions number is same, they are 1 to 1. So our nucleus want to attract all nitrate ion to neutralize the charge of the silver. But except adsorption force, there are one more force, diffusion. Try to uniformly distribute nitrate ions in this colloidal solution. So that's why as a result of these two forces, there will be two layers formed. Part of nitrate ions stay adsorbed on the surface of nucleus. If total number of nitrate ion n, to show that part of nitrate ion adsorbed, we use this n minus x in brackets. So part of nitrate ion adsorbed, and because of their adsorbed, they're still solid crystalline. It's still solid, still crystalline, still charged because of not all nitrate ion adsorbed on the nucleus surface, and it's still charged positively. Let us see what is the charge of this particle. This particle is, sorry, I will indicate like this, and one more. So nitrate ion, after it's adsorbed, its absorption layer of opposite ions, minus n minus x charged, minus n minus x. From silver plus n, if you will take sum of these two charges, plus n minus x, you will see that charge of the granule, this is solid particles, nucleus plus adsorption layer of opposite ion, known as granule. It's plus X charged. And the rest of nitrate ions staying outside in diffusion layer. That means they are not adsorbed. They are present around, like moons around planet, being not on the surface but close enough as a diffusion force and adsorption force in equilibrium. So these ions, how many of them? X, n minus X here inside being adsorbed, and that means the rest of nitrate ion, X outside. This all particle, still solid crystalline, it's a micelle. It's neutral. Neutral particle, colloidal particle of hydrophobic colloid. Outside micelles, quite often in aqueous medium, they are they attract water molecules, forming water layer. Water is not a component of micelle. It's just formation of hydrates as an ionic solid. And one of the factors stabilizing the structure. So such way, it's just a formal picture of colloidal particles. Such way colloidal particle can be imagined. So take a look, silver iodide inside, then silver positive adsorbed on it, part of nitrate ion adsorbed, forming nucleus, and in a blue layer, the rest of nitrate ion staying close to the surface but not on it. This is diffusion layer, and water around. So dipole plus charge to the minus part of the colloidal particle. Number of nx and number of water layers are just hypothetical values. So as a result of all these factors, adsorption, diffusion, they are formed electrical double layer formed. So if there is silver nitrate in excess, there will be what I told you, positive charged granule and negatively charged diffusion layer. If there will be potassium iodide in excess, the micelle will look different. Take a look how it's mentioned. Same reaction, silver iodide formation. That's why aggregate still same, but on the surface of this aggregate will be adsorbed not silver, but iodide ion as potassium iodide in excess, and only ions which already inside the aggregate and in excess can be adsorbed, forming potential determined layer. So iodide ions inside adsorbed, and then potassium forming oppositely charged layer. So adsorption layer of opposite ion and diffusion layer of opposite ion. And the charge of the granule is negative here. Take a look. Granule, it's our nucleus together with a part of adsorption layer of opposite ions. And it's still negative because of not all potassium adsorbed. Still negative. And this is diffusion layer and water. So other ions, right? So what here important to understand? This difference in potential, it's an electrical double layer. Here can be electrical zeta potential and phi potential. So take a look. Potential on the boundary of solid phase on the nucleus. So take a look here. After a neutral aggregate, adsorbed potential determinant, their first charge appears. This is phi. And then zeta potential, it's electrical kinetic potential on the interface between adsorption and diffusion layer. Between adsorption and diffusion layer. That's mean here. Because of this electrical double layer, there are some list of properties for colloidal solution typical because of the charge. They are known as electrokinetic properties because of electrokinetic potential. Electroosmosis, electrophoresis, quite familiar word, striving potential and potential of sedimentation. Let us see what's happened then. Electroosmosis. It's a movement of liquid dispersion medium through the immobile dispersed phase, which is usually porous material. That means dispersed phase shouldn't move, but dispersion medium do. As there are ions present in dispersion medium, that's why it's clear we need two electrodes dipped. And as a result of this electrodes present, we have movement of oppositively charged particles too. So it was, let us take some colloidal solution with a porous materials with our dispersed phase particles charged positively, like in our first micelle structure where was silver iodide with a silver salt on it. It was positively charged. And it fixed in the porous material, that means can't move anywhere. But in diffusion layer, there are present negatively charged particles. And for example, in our case, there it was nitrate. So that's why if we dipped electrode in this colloidal solution, as a result, negatively charged move to the positively charged, and we see what we see. Liquid dispersion medium moves together with diffusion layer to the positively charged electrode. If there will be no porous materials, there will be two-side movement. This is electrophoresis. It's a movement of dispersed phase particles in electric field. Diffusion layer moves to the one, granule moves to the opposite. The rate of the speed of movement depends on value of zeta potential. As higher, as faster the rate. As a result, stability of colloidal particles destroyed because of we separate granule from diffusion layer which formed neutral micelle. No, and that's why their stability is lost. Streaming potential and potential of sedimentation are factors opposite to electroosmosis and electrophoresis. There was a movement was a result of we have electric field. We made it. But can be situation we make solution, colloidal solution, moves and voltage as a result of this movement appears. So streaming potential, it's appearance of voltage when liquid dispersion medium flows through a porous immobile dispersed phase. So we make our dispersion medium pass through the porous material, and the place, because of our example was nitrate ions there were, so negatively charged dispersion medium, it passing through, and the place it goes become exactly charged. If minus goes there, minus they appears, leaving plus behind. Now, for example, in arteries, because of their colloidal solution, there are such streaming potential present. Small one, as you can see, but present. Potential of sedimentation, it's appearance of voltage when dispersed phase particles settle down under the gravity. If somehow sedimentation will happen, so particles settle down under the gravity with a different rate, depends on size. And that's why, due to what is the granule charge, what is the value of zeta potential, there are different voltage pairs. The lowest part can become plus and upper one minus, or minus plus opposite. So due to what the initial colloidal solution was. But it's a short time, short and quite small value. So why colloidal solutions are stable? As I told you, hydrophobic, they even prepared no direct method. Substances insoluble nature present there in colloidal state. Why they not settle down under the gravity? Why to make them precipitate we need to use some stressful factors? Because of there are some stabilities. So ability to maintain constant distribution of dispersed phase particles in a dispersion medium, it's a stability of colloidal solutions, and there are two reasons: sedimentation resistant and aggregation resistant. Sedimentation resistant, it's a stability of colloidal to settle out under the gravity. They are not precipitate because of the gravity. Why? The main reason of this, it's a Brownian movement. Brownian movement. It's a motion without resulting force looks down. It's a chaotic motion. So random. And that's why till Brownian movement there. Colloidal particles will not precipitate. This resistance can be affected by viscosity of dispersion medium, definitely density of dispersed phase and dispersion medium, absorption of molecules stabilizing dispersed phase structure. If we will absorb them, they disperse, then no stabilizing agent more, and their precipitation happens same moment. So it's possible to destroy using stressful factor. But till Brownian motion there, a Brownian motion till size of dispersed phase particles from 1 to 100. Same moment it becomes bigger, Brownian motion stops and sedimentation starts to happen. Why they are Brownian motions? Why they are 1 to 100? Because of the aggregation resistance typical. So it's ability of colloidal system to save their size of particles from 1 to 100. It's resistant to form aggregates. We know that growing of crystals is spontaneous process, but somehow they are not aggregate, they are not grow. Why? The reason is presence of electrical double layer. Our particles, colloidal particles, they are same charged. Positive nuclear, negative diffusion layer, or negative nuclear, positive diffusion layer. Same charged particles can't attract to each other. That's why till electrical double layer there will be no aggregation. Same moment, aggregation, this electrical double layer will be destroyed, aggregation starts to happen, and particles becomes bigger size, and same moment precipitate because of sedimentation resistance is destroyed as well. So how to cause aggregation resistance? Addition of electrolytes is the easiest case. We can add positively, negatively charged particles, can neutralize the charge of the granule, and same moment granule becomes neutral. There are no electrical double layer finally. Temperature can end the electrostatic repulsion of colloidal particles if it will be stopped by neutralizing granule. We will get aggregation resistance. So irreversible aggregation of colloidal particles known as coagulation. So coagulation, the easiest way to cause coagulation is additives of electrolyte. And here, if there are one electrolyte, we know that there are cation and anions, a true solution definitely supposed to be. Their Schulze-Gardy rule help us to understand which one, cation or anion, in this electrolyte cause coagulation. So first one, if there are one electrolyte, coagulation of colloidal particles caused only by ions or positively charged to the charge of the granule. Not all electrolyte, not all, just ions or positively charged to the granule. So if granules positively charged, only an ion of electrolyte can cause coagulation. So if they are negatively charged granules, that means positively cations from electrolyte we add cause coagulation of colloidal particles. If there are fewer electrolytes we have, and we need to choose the one with a greater coagulation ability, with a smaller concentration, smaller value of electrolytes cause coagulation faster. So we will continue with the second part of the Schulze-Gardy rule. The ability of electrolytes to cause coagulation of colloidal solution increased with the increase of the ion charge. So if there will be aluminum chloride, barium chloride, potassium chloride, and we need to choose which one the highest value coagulation ability or negatively charged granule, aluminum will, with the same concentration, will cause coagulation much faster because of the charge +3, and it will attract much bigger rate to negatively charged granule, and that's why coagulation will be much faster. If they are positively charged granule, there we will compare anions, and sodium phosphate, sodium sulfate, sodium chloride, we will choose sodium phosphate because of their phosphate ions 3 minus charged. And can be case if they are both few electrolytes with the same charged cation or anion. How to choose which one in this case will cause coagulation faster. When charge of coagulant ion is the same, their coagulation ability is increased with increase of the ion size, reduce. And here it's easy if you know periodic table rules. They are as low in periodic table inside the group as big as the size. So that's why barium, the biggest size from all of them, calcium and magnesium. If we will deal with halogens, for example, we know that fluoride ion is the smallest one, iodide the biggest one, and it's possible to choose which one the greatest value coagulation ability. So for example, if we deal with electrolyte, potassium nitrate as we want to use as coagulant, the substance will cause coagulation. First of all, colloidal solution must be prepared. So it's done, it's for example not silver iodide but silver chloride. There was taken this solution prepared by excess of silver nitrate, and that's why the granule is positively charged. So how to cause coagulation? We need electrolyte, it's an inert electrolyte, chemically will not react with none of the initial substances. So not potassium but nitrate ion excess after colloidal solution is prepared will lead to coagulation because of more nitrate ion means more nitrate ion adsorbed on the surface of nucleus, and one moment the charge becomes zero, granule charge becomes zero, and the oppositively charged ions leaving behind particles able to coagulate. That means attracts. So what is coagulation threshold? The least value of electrolyte concentration that cause coagulation of colloidal particles known as coagulation threshold. As higher the coagulation threshold, that means we need less electrolyte to cause coagulation. Take a look. Coagulation ability, it's a value opposite to threshold of coagulation. It's measured in liters of colloid that can be coagulated by 1 mole of the electrolyte. So opposite to threshold. That means as lower the coagulation threshold, as least value of electrolyte we need to cause coagulation, as high the coagulation ability of this electrolyte. So one more thing from this lecture, it's a colloidal protection. I want to tell you one more thing. For some lyophobic colloidal solutions like liquid, that means emulsions, as you know, I told you that they are supposed to be immiscible liquids to form emulsion, and such emulsions are very unstable. Here we can't use electrolytes to stabilize such type of colloidal solution. There are other substances I use, high molecular weight compounds with a polar head, non-polar tails. It's such a way to stabilize colloidal solutions known as colloid protection. It's a phenomenon of increased instability of colloids under the addition of high molecular weight substances known as polymers. Well, this is enough in this topic. Let's talk a few words about pH, because of some students will have this class soon. Maybe even this week. Some already pass, but still need this information for checkpoint number 2. Essential topic: solutions of electrolytes, pH and buffer solution. Information will be quite fast, half an hour we have. So to put your attention on some of the most important things. So electrolytes, compounds which dissociate into ions when dissolved in water, and that's why they conduct electricity. They can be salts, acids, bases, Electrolytes can be strong, can be weak, can be medial strong. Let us see, in all cases, they dissociate into ions, or completely or not. The behavior of electrolyte described with Arrhenius theory of dissociation or ionization. What is the difference between these two words? I will show you them. So first of all, when electrolyte is dissolved in water, it splits into ions, positively and negatively charged. Van Hoff's factor, isotonic coefficient, we already mentioned in solution topic. It shows how well this electrolyte dissociated because of it shows real number of particles appears after electrolyte dissolved in water medium. So for non-electrolytes, even being soluble, isotonic coefficient, Van Hoff's factor is 1 because of number of particles we expecting according to the concentration equal to number of particles really we have measured experimental way. For electrolytes, it's not so. If electrolyte dissociate completely and there are no interionic interactions, we can say that number of particles 2, 3, 4, 5 times higher. Usually, if not completely dissociated, we have mixture of molecules not dissociate and some number of ions are formed over some total number of particles supposed to be according to the concentration. Dissociation or ionization is a reversible process. That's why if we deal with ionization, association can happen, but when we deal with a strong electrolyte, backward arrow, ionic solids dissociation. Backward arrow doesn't mean that they are formed initial ionic solid. No, backward arrow means interionic interactions. They appears always, except ideal solutions, and that's why we affect the final experimentally we measured dissociation degree and other factors. So according to dissociation degree alpha, electrolytes can be strong, but the problem is electrolytes, strong electrolytes dissociate completely, 100% they're supposed to be. But because of interionic interactions, as I told you, real value we measure, it's less than 100, and to be strong enough to be more than 30%. It's quite affected by concentration. As lower the concentration of strong electrolyte, as higher the value of dissociation degree. As in the ideal case, it says 100% will be measured one. As example, any strong acids, you must know all of them. Strong bases, alkalis, sodium, potassium, barium hydroxide dissociate completely. No, and soluble salts, all of them are strong electrolytes. Weak electrolyte, they have dissociation degree less than 3%. No, and here any weak acid, acetic, carbonic acid, ammonia, which is ammonium hydroxide, here can be measured. It's a weak but soluble weak base. And the middle strong are between strong and weak. First step dissociation of phosphoric acid is a middle strong. Second, third, they're already weak part. Alpha from more than 3 but less than 30%. How to understand the difference between ionization and dissociation, and they're quite often mentioned in the same sentence. So dissociation of ionic compound happens. So if the ions already there, that means this is correct word for ionic solids. For example, sodium chloride. Sodium chloride is ionic solid where in crystalline structure already ions are. They are sodium plus and chloride minus. They are not formed after we dissolve substance in aqueous medium. Water just helps them to be released. Splitting happen, not formation of ions, but dissociation into ions. In aqueous ions, they are going in aqueous medium. For molecular compound with a covalent polar bond, first of all, the ions are not present yet. They are covalent bond. Ions should be formed, and water, as a plus minus charged, it's dipole. It leads to ionization when it's attracted to the polar molecule. For example, HCl, it's not a ionic compound, it's a molecular nature compound. They're covalent polar bond, quite polar, but covalent polar. Water leads to ionization happen because of positive part, that means the hydrogen part, it's trapped to the negative part of HCl, and oxygen part to the positive part, to the hydrogen part of HCl. So as more water molecules here, as more polar the bond, and one moment it becomes ionic. Same moment molecule is ionized, it dissociates into ions. That means, see, ionization, then dissociation. Just dissociation for ionic compounds only. That's why dissociation itself never happens step by step for ionic solids. They are just, ions are present, that's why we dissolve in water medium, they are released free. For molecular compounds, as ionization, it's a step-by-step process. Dissociation for them also can happen step by step. For example, for HCl, it's a one single step. There one covalent bond to be ionized. But if there will be carbonic acid, H2CO3, there will be two steps. For phosphoric acid, three steps dissociation because of three steps ionization. What factors can affect this dissociation? Is it good or bad happen? So first of all, in all cases, dissociation is a chemical process. That's why its effects depends on nature of the substance. Some electrolytes, because of their nature, the nature of the bond, the ability to be polarized by exact solvent, they can be strong or weak, and nature can't be changed. If we know that for same concentration, dissociation degree for acetic acid it's 1.32, for HCl, hydrocyanic acid, it's a 7 times 10 power negative 3. It's a very small percent. See, it's very, very small. And if we will check other factors, also can show us how well this weak electrolyte dissociate or how bad. Dissociational constant, we will see that. What is it? We will see for how many times HCl acid dissociational constant, which is 10 power negative 10, smaller than the dissociational constant of acetic acid, which is 10 power negative 5. 10 power negative 5, or here 10 power negative 10. Quite big difference. Second factor after nature, that's mean nature of the bond, nature of the solvent, so concentration of solution. It's a second factor. Oswald's dilution law, mathematical expression I will show you later. But it stated that as lower the concentration, as high the dissociation degree. Because of it's supposed to be clear. Interionic interactions not allow substances dissociate such well, and even ionization happen not such effective because of higher concentration of solute means lower concentration of solvent. Temperature next factor. As higher the temperature, as higher the dissociation degree. Because of temperature always increase the chemical reaction rate. Dissociation is a chemical process. So equilibrium constant of equilibrium between ions of weak electrolyte and unionized weak electrolyte, known as dissociational constant. Equilibrium constant, because of their reversible process, dissociation, association. That's why this equilibrium can be shifted. Take a look for the easiest case, mono-basic acetic acid. It's a weak one acid. So it dissociates, definitely not completely, because of it's a weak with dissociational constant 10 power 1.76 times 10 power negative 5. But it's equilibrium constant. That's why if it's equilibrium constant, the value of Ki equal to mathematical product of concentration of products or mathematical product of concentration of reactant, undissociated one. So, and these values are tabulated. So that's why you shouldn't memorize this value, necessary just to open the appendix page and be ready to deal with. So for some acids, as I told you, the monobasic ionization happens single step, dissociation. That's why one single step happened. But for diabasic, triabasic acids, dissociation happened step by step because of ionization. And let us see the difference between. Carbonic acid, it's a weak acid. First step, So first of all, because of when in water medium, because of water molecules effect, one of the bond, OH bond, ionized, and dissociation happen in the proton and hydrogen carbonate ion. Mathematical product of concentration of product of a mathematical product of concentration of reactants, that means the molecular form of carbonic acid, give us 4.5 times 10 power negative 7. It's quite small. It's a weak acid, weaker than acetic. But there's still OH group, but not as polar as it was when there were two OH group in initial. That's why it ionized already weaker way. And that's why dissociation second step much smaller. It's 10 power 4 times smaller than dissociational constant for the first. The average chemical reaction, it's a hypothetical because of we can see that mainly hydrogen produced due to first step dissociation. Second one, for mathematical calculation, we can even ignore in some cases. So water itself, it's an electrolyte. That's why it's also dissociate in proton and hydroxide ion, same number of moles. So that's why equilibrium constant for this water dissociation also same as in previous cases. It's a mathematical product of concentration of products or mathematical product of concentration of reactants. So what we see here, this dissociational constant, it's a very small value as water very weak. It's a self-ionization of water happen very poor. It's equal 1.8 times 10 power negative 16. You can imagine how small it is. But as we know that if temperature is constant, water concentration is constant. We can't say that today water more diluted than it was yesterday. No, water is a constant, and this value 55.56 mole per liter. As well as we can say that dissociational constant 1.8 times 10 power negative 16 is a constant and water constant. Their product supposed to be constant as well. Product of dissociational constant of water and concentration of water at standard temperature. If you will multiply 1.8 times 10 power negative 16 times 55.56, you will get 10 power negative 14. This value also constant and known as ionic product of water. So mathematical formula of ionic product of water, Kw, it's a mathematical product of proton concentration and hydroxide ion concentration. It's true for every aqueous solution and equal to 10 power negative 14. So if the concentration of H plus and concentration of H minus are equal to each other, there will be each one 10 power negative 7, that means pure water, their product 10 power negative 14. So deal with such values like 10 power negative 5, 10 power negative 7, 10 power negative 11. It's very hard for calculation. That's why it was recommended to use other values to explain how acidic or basic the medium there. It's a pH scale. Everyone knows the pH scale. pH, it's a minus log, decimal log of concentration of proton. Minus decimal log. Small p, capital H, pH. So according to this information, what we know? For natural solution, for neutral solution, it's when 10 power negative 7, just told you, proton and hydroxide ion, pH equal to 7. As minus log of 10 power negative 7, it's a concentration of H plus. pH equal to 7. More acid, H plus more than 10 power negative 7, give us less pH value than 7. The minimum is 0. There can be now found some substances with a pH less than 0, but it's not because of the aqueous medium itself dissociation. There other processes happen. So, and if there are more base, if there we will drop few sodium hydroxide drops in water medium, we will get less H plus concentration, but more H minus concentration. And pH will be more than 7 because of minus log. So when there is solution of acid given, there we can find H plus concentration because of it produces proton. But when we deal with a base, sodium, potassium, barium hydroxide. They are H plus, not mentioned concentration in the formula. So we need to find it. How can we, if we're interested in pH for sodium, potassium hydroxide? We know that except pH, their pOH scale also present. pOH, it's a minus log of concentration of hydroxide ion in the aqueous medium. As a ionic product of water, it's a mathematical product of concentration of proton and hydroxide ion. If we will take minus log of left side and right side same moment, we will get same ionic product of water, but minus log of H plus, it's pH. Product of logs, it's a summation of, that means plus minus log of OH minus pOH, equal to 14. This is also true always for aqueous solution. And if their base is given, sodium hydroxide, we can find concentration of hydroxide ion from initial. We can find pOH first, and then pH, if we're interested in, we will find as a 14 minus pOH. There are some list of biochemically important liquids you must know this semester. You will need these values then, next year, after next year, and so on. That's why better memorize already now. Blood plasma, it's a 7.4, slightly alkaline. More correct to say 7.4 plus minus 0.05. This is the value of normal pH of the human blood. 7.4 plus minus 0.05. That means the interval of normal is very small. It's from 7.35 to 7.45. Saliva, this is slightly acidic medium, as you see. Gastric juice, strong acidic medium because of HCl acid. Urine is a unique liquid from acidic to weak basic through neutral. That's why pH of urine only together with some other characteristics can help us to make conclusion. What is the problem? Spinal cord liquid unique because of it's the same pH and the blood plasma, same as 7.4 plus minus 0.05. So for blood, if there's shifting of pH from 7.4 any direction, more acidic, more basic, there will appear or acidosis or alkalosis. What is acidosis? It's a shifting of pH of the blood in acidic medium, lowering from normal value. 7.35 to 7.45, it's a normal, it's a compensated. We have substances present in blood which neutralize this shifting, not allow. pH shifts more. We will see then how to name these substances. What will happen if pH will be shifts lower than 7.35? Acidosis. And the final shifting of pH, delta pH, is 0.6. There are serious problems with health, paralysis, coma and death. No paralysis, no, coma and death. Death will happen 6.8 shifting. It's very small shifting. Alkalosis, it's a shifting of pH of the blood in basic medium, increasing from normal value 7.4, and alkalosis not appears too often. So when shifting of pH in higher values than 7.4, the highest one 6.8 already. So it leads to death. What is the reason of acidosis alkalosis can be? There are classification of acidosis alkalosis. If you're interested, you can find in internet even. Can be different reason. It can be gas acidosis alkalosis, can be metabolic one. Respiratory can be. So what mean respiratory acidosis alkalosis? That means there's something wrong with the air we breathe. For example, acidosis can appear if we breathe air with a higher concentration of carbon dioxide air or higher pressure. So carbon dioxide dissolves more, forming carbonates, carbonic acid, and that's why their acidity rising. Or asthma, where the problem was with breathing out, carbon dioxide is concentrated in the blood, it's acidosis. Diabetes mellitus also, it can be a problem, leads to acidosis, one of the symptoms. Alkalosis more often happened it's hyperventilation of lungs. You will read in class time, we will discuss, but quite often happen because of hospital mistakes. pH of solution we use for intravenous feeding should be same as pH of the blood. Do not lead to acidosis or alkalosis. Not only osmotic pressure of solution should be same as osmotic pressure of blood to prevent hemolysis or plasmolysis, but pH as well is supposed to be equal to the pH of the blood, 7.4 average. So that's why sodium hydrogen carbonate we add to the solution we use for intravenous feeding, because of its as a result of hydrolysis leads to slightly alkaline medium. So it's very important. So mistake in a calculation, mistake in a solution, if we will get more alkaline medium than 7.4, it can lead to alkalosis due to intravenous feeding. So before to explain factors affecting our pH resistance, there I want to remind you just a few things about solubility of insoluble electrolytes. That absolutely insoluble substances not exist, and even some mentioned as insoluble in solubility table, they are still dissolves a little bit, and that's why as the ionic solid nature, the small one, almost negligible part which is dissolves, will dissociate completely, and there we will get the equilibrium between insoluble part in the left side and ions present as a result of small part of the substance dissociate. And this is same dissociational constant, but we know the solid substance is not in the rate law. They are not in the rate law. As a result, their known denominator are just a mathematical product of concentration of products in power of balance coefficient as equilibrium here. In denominator, nothing as its solid substance. Such equilibrium constant known as solubility product, and these values are tabulated as well. For example, if you need to find solubility product of lead iodide, it's also insoluble yellow colored precipitate. If we need to determine what we should do. Solubility product of this lead iodide, it's a mathematical product of concentration of ions formed due to dissociation of this small part of the soluble part of the salt. So in the power of balance coefficients. So as orders here equal to balance coefficients. And if we accept solubility, that's mean concentration of dissolved substance is equal to X, or capital S, it's a symbol of solubility, as you remember, I hope. So according to stoichiometric coefficient, number of moles of lead iodide equal to number of moles of lead 2 plus. That's why the concentration of dissolved part of lead iodide equal to concentration of lead 2 positive. For iodide ion, 2 times higher. That's why when we take power, we get 4 concentration of initial S power cube. And if we know that solubility product, they are tabulated, it's 1.1 times 10 to the negative 9, we will find cube root necessary to be attentive with a unit, as its solubility, it's a concentration, and that's why mole per liter unit. What then? For strong electrolytes, few words. It's a behavior of strong electrolyte, it's a little different from weak, it's clear. They are the strong electrolyte theory. According to this theory, dissociation degree of strong electrolytes is unity, 100%. But because of electrostatic interactions, interionic interactions, in solution of strong electrolytes, their alpha we measure experimentally will be lower than supposed to be. I told you more than 30% already. So how to describe how well this electrolyte dissociation degree can be. But each one electrolyte, it has ionic strength. For dilute solution, it works good. For concentrated, not. So ionic strength I, it can be symbol I, can be symbol mu. So it's a half of summation of mathematical product of concentration of ion times charge square. For example, if they are strong electrolyte, any soluble salts are strong electrolytes, potassium sulfate with a concentration 10 power negative 2 mole per liter. Due to dissociation, again, backward arrow here means not formation of molecules, it shows interionic interactions. So what about interionic interactions here? And dissociation, no, dissociation first. Due to complete dissociation as an ionic solid, 2 potassium positive ions formed, and that's why concentration of these ions 2 times higher than concentration of potassium sulfate. And sulfate ion is a 1-to-1, that's why 10 power negative 2 mole per liter as well. So to find ionic strengths, we should start with the formula and then apply this formula for our exact case. A half, then we need a summation. That's why brackets made and better to use. So concentration of first ion, potassium, 0.02 times charge of potassium square, plus concentration of second ion, sulfate ion, 0.01 times charge of this ion square. No, it becomes positive then. If we will open the brackets, if we will divide 2, we will get 0.03. 3 times 10 power negative 2. So, and to remind you this, it's a very short information before to show you how to write hydrolysis. I don't know why it was a big problem for some students to do. So there's 3 theories of acids and bases we will deal with, and now we're dealing with only first of them. It's Arrhenius theory. Laurie or Lewis theory, we will deal with the next part. It will be a second part of the chemistry, some submodule, second submodule already. It's organic chemistry. There we will talk about proton donor, proton acceptor. Now Arrhenius theory. According to Arrhenius theory, acids are electrolytes produced due to dissociation, only one type of positively charged ions. They dissociate forming protons. But it's important, Arrhenius theory, it's a theory dealing with electrolytes. Bases are electrolytes dissociate in aqueous medium, forming hydroxide ion is the negatively charged ions only. So what is here? When we deal with acid and base themselves, it's clear. One dissociate forming H plus like HCl, H2SO4. Sodium hydroxide, barium hydroxide dissociate forming OH minus, and that's why they're acids and bases, and that's why pH medium can be acidic, can be basic. But there are some substances, as you know, salts, there are no H plus or H minus in the formula, but somehow when they dissolve in aqueous medium, they are change pH into acidic or basic. Can be no changes, but can be. This happens because of when substance dissolved, they chemically react with a solvent. For salts, it's also possible. Chemical reaction of salts with water, known as hydrolysis. Hydrolysis not only for salts happen, huge number of organic compounds chemically react with the water. So hydrolysis of salts is reaction of salts with water to produce acidic, basic or neutral solution. So there are 4 types of salts, but 3 types of hydrolysis. What types of salts can be? According to the how strong salts, it's a result of neutralization reaction, we can say. They are cation combined with anion. If cation can be from strong or weak base, and anion can be from strong or weak acid. That's why 4 types of salts. The first one, salts of strong base and strong acids. Strong base is not so many. It's a sodium, can be potassium, barium, lithium. Acids, strong, you must know there are 6 you need to know. It's HCl, HBr, H2SO4, HNO3, and which one I miss? Hydrochloric, hydrobromic, nitric, sulfuric, chloric to chloric, 6. So these substances, when they combine together, strong and strong, they are forming exact salts like sodium chloride, potassium sulfate in this case. When we dissolve the substance in water, what's happened? It seems like they should react with the water to form backward to neutralization reaction forming product HCl and sodium hydroxide. But if we will write what's really happened when we dissolve ionic solid in water, we know ionic solids are present as separate ions, sodium plus Cl minus in water, and we know that strong electrolytes dissociate completely into ions. That's why it must be written as separate ions. We should cancel some ions not react chemically, and that's why can exist simultaneously in solution. We will get only one thing, we will get self-ionization of water. That's why when we deal with the salts of strong acid, strong base, their pH equal to 7 because of no hydrolysis happen. Hydrolysis doesn't happen. That's why pH equal to 7. In other cases, there will be some chemical reaction and some changes may have. So salts of strong base and weak acid, for example, sodium acetate, strong base, weak acid, potassium sulfide, and some other. So what's there happen? Again, molecular equation backward to neutralization. Sodium acetate with water supposed to form acetic acid and sodium hydroxide. Again, ionic solid should be written as separate ion. That's why ionic equation now. So we will see that strong electrolyte among product, only one. It's a sodium hydroxide. That's why it should be written as separate ions. Weak electrolytes in ionic equation, we never write as separate ions. This you must know. So, and that's why they are present what? H2O we leave as a molecular formula and acetic acid as well. So what we need to cancel? Just sodium. And as a result, we will see that only acetate ion react with the water, forming acetic acid and OH minus. So it seems like, take a look, strong part not react with water, but reason of what medium? It was strong base, basic medium, because of weak acid. Seems like busy reacting with water. The next situation if there will be strong acid and weak base. Again, for example, ammonium chloride or aluminium bromide or something, same, ammonium sulfate. Strong and weak, strong acid, weak base. Same, we write molecular, then ionic reaction where weak base, ammonium hydroxide, it can be written as ammonia just. We can't write as a separate ion, as it weak one. Only strong electrolytes should be present as separate ions. We cancel chloride ion, and we see that they are only weak base cation chemically react with the water. Strong acid part not react with the water, but forming the medium. As it's salt of strong acid and weak base, the medium will be acidic. The situation will be not so easy to make conclusion without extra factors given when the salt of weak acid and weak base. When both are weak, to make conclusion which one stronger, to predict the medium, we need to use the values of dissociational constants tabulated, and what we can find there. If Kb more than Ka, that means both are weak, but base slightly stronger than acid, there will be basic medium. If Ka more than Kb, that means both are weak, but weak acid slightly stronger than weak base. It's a less than 7 and can be case when Ka equal to Kb. This is what given here. Ammonium acetate, it's a such salt. Hydrolysis happen, ionic equation we can't write because of their water, ammonium hydroxide and acetic acid, we will not write as separate ions. For this salt, Ka, it's a 1.76 times 10 power negative 5. For ammonium hydroxide, it's 1.74 times 10 power negative 5. They're approximately equal to each other. That's why hydrolysis happen, but pH doesn't change significantly. So clear, we have solution of weak acid or weak base, strong acid, strong base, or solution of exact salt as a result of hydrolysis, their pH is different. So reason of pH different from neutral because of addition of some acid or base, or addition of substance can leads to pH change. But there can be solutions. We add acid, we add base there, but pH doesn't change. So it's supposed to be because if we add proton, we add hydroxide ion, but no. Such solutions are known as buffer solutions, and solution whose pH value doesn't change significantly upon the addition of small amounts of strong acid, bases, and water from outside. So, what is here necessary to know about buffer solution? It's supposed to be not one substance in a mixture. They're supposed to be mixture of at least two. So for two-component buffer solution, there can be acidic buffer solution. It's a mixture of weak acid and its salt with a strong base. For example, acetic buffer. It's a weak acid, acetic acid, and sodium acetate. Carbonate buffer, it's a mixture of sodium hydrogen carbonate and carbonic acid, which is weak. So weak acid and weak acid and weak acid anion. And can be basic buffer. It's a mixture of weak base and its salt with a strong acid. So that's mean weak base and weak base cation. As example, you should know only one ammonium buffer. Because of ammonium hydroxide, it's only one weak base soluble we're dealing with in inorganic chemistry. I think I will show you just, and that's it. There are a few minutes left. So, principle of buffering. What is the idea? One of the components should neutralize acid adds, and one of the components neutralize base. This is the idea. That's why two components. So, acetic buffer solution, acetic acid and sodium or potassium acetate. If we add strong base, few drops, if we will add a lot, there will be change in pH, definitely. So, we add sodium hydroxide to acetic buffer. Sodium hydroxide will react with the acid. Neutralization reaction happen. So to form salt and water. If we will write ionic, we will see that OH minus should be neutralized by acetic acid. So neutralization reaction happen. So that's why pH doesn't change significantly. Why would significantly here necessary to use? Because of neutralization reaction, it's a reversible process. As you know that their equilibrium is reached. And that's why backward hydrolysis will happen a little bit, but will. That's why pH doesn't change significantly. What about addition of strong acid? Also few drops. The second component of buffer solution, so acid neutralize alkali, a salt will neutralize strong acid. What's happened here? As a result of reaction with strong acid, their new acid is formed, weak one, that's why reaction happened, and the sodium chloride. If we will write ionic reaction and we will cancel sodium and chloride ion, we will see that acetate ion react with proton from HCl acid, forming acetic acid. Also clear that it's not strong acid anymore, it's not strong, but weak acid also should change pH. Why here pH doesn't change significantly? Because concentration of acid, weak acid already present in this solution appears. So same acid is produced. That means due to this reaction, concentration of acetic acid is rising. According to Oswald's dilution law, dissociation degree is a square root of dissociational constant over concentration of acid. I'm sorry, I think lecture is over. I will try. So, concentration of weak electrolyte rising, dissociation degree lowering, and that's why pH doesn't change significantly. So I'm losing my voice, I'm sorry. So that's why. And time already, half of minute left. So lecture is over. One thing I will show you for you to copy, it's a buffers of human blood. Just indicate for yourself that the main buffer solution of human blood is carbonate buffer, the main one, but blood plasma, main one, not whole blood. Phosphate buffer second in plasma, and protein buffer the third one. But for whole blood, hemoglobin buffer is the main buffer solution. Resist change in pH. That's why our blood pH doesn't change significantly when we breathe air with a higher concentration of carbon dioxide if a little one, and other factors also. Their buffer solutions resist change in pH. Okay, goodbye. Lecture is over.